Okay, this is then the third lecture, and last time we talked about more things. We ended by talking about the exponential map, which went from the matrices n times n matrices into the general linear group. It was continuous. And it was well, and then obviously then well defined. If I'm writing it as defined on the entire matrix space, it means that it's well defined for any matrix. And we talked about the fact that it was surjective for when this was the complex numbers, and it was not for the real numbers. We also talked about this fact that if xy was equal to yx, then the normal exponential rules hold, namely that it doesn't. I can write the exponential, the sum of the exponentials, the exponential of the sum, sorry, as the product of the exponentials. And it doesn't matter which order I'm doing it in. So in particular, E alpha x times E beta x is equal to E alpha plus beta, and E of minus E to the minus x is equal to E minus x inverse. So these are the things that we talked about last time, and these in particular look like sort of some important properties that we know of similar, where this operation multiplication here becomes a plus here, and like inverses go to inverses. And these, if you remember from your algebra class, this looks like something like a homomorphism, right? And so we haven't really taught, someone, I can't remember who told me that, we haven't really talked about Lie algebra homomorphisms. So let's do that, because it will lead to a nice, it has a nice relationship with this exponential map. So definition, so if G and H are two matrix groups, then a map going from F to H is called Lie group homomorphisms. If it is continuous and a group homomorphism. So that means that f of A times B is f of A times f of B. So remark, so since level sets are closed, the kernel of F, so all A in G that are mapped to the identity in H is a matrix Lie group. So just like for normal groups, the kernel is an example of a matrix Lie group. This is not necessarily true for the image of F. So collection of all of F of A where A is in G. So so the problem is that so level sets are closed if you take or more generally the inverse mapping on sets is closed for a continuous function, takes closed sets to closed sets. A map going forward, if it's continuous, does not need to take closed sets to closed sets. So so the counter example, counter is probably with a U, right? That we've seen before. So what I could do is that I could take GL1R, or I can even do the connected component. So GL10. So last time we talked about connected components. So these are the ones that could be connected to the origin by a curve. So in here, these are just for, we haven't, these are elements in GLR such that the determinant of A is positive. So we talked about last time that the real general linear group is actually not connected because it has two components, one for positive determinant and one for negative determinant. And we proved last time that it has at least two components, but these are in fact the only things we have. But we can write as what this means is essentially that we have something like this, where R is a real number. So for all intents and purposes, this is the real number line. I'm just writing it. So since we sort of pushing everything into this format of matrix Lie group rather than general Lie groups, I'm just writing the real line as a matrix Lie group. But like you could just write R. You could just write R with plus if you're comfortable with the multiplication not necessarily being matrix multiplication. Okay, so then let me this be my group G, and then my group H could be, let's make it GL2C, for example. And then I define f of E R as this thing we looked at before, I to the power R, 0, 0, I, S, R, like this. For our real, where S is irrational and fixed. So some fixed irrational number. And then we saw that the image, sorry, then we saw the first time when we looked at the example that this was an example of a subgroup that was not an actual matrix C group because it wasn't closed. So this will then be an example of the case where the image is not a matrix C group. So the reason I'm bringing it up is I'm going to do now several results about the exponential where I'm going to let you read the proof on your own. But one of these results will depend on this idea of a group homomorphism. So the theorem so first of all, we have A that for any let's say complex matrices could also be real. Let me just put K here so that it doesn't matter. We have E of X plus E of Y equal to I'm going to infinity of EX EY M Y to the power of M. So this is boring to prove, but we will need it later. So this will show up again in hopefully next week or in 2 weeks when we're talking about the Lie algebra of matrix Lie group. So where the whole idea is that it's important that we can construct a plus using, so on this side, there's the plus. Here, there is the matrix multiplication. So it's this idea that we can reconstruct the plus using the matrix multiplication. And the other thing that I'm not going to prove is the following. So suppose that we have something like this, a continuous, so it's essentially something that it's something similar to the example I've just shown. So if we have a continuous map, so it's a continuous group homomorphism. Let's write it like F, just to make it match from before. Homomorphism. So that means that like F of R plus S, or let's say T plus R is F of T times F of R. Then where G is a matrixly group, then there exists an X in complex matrices such that F is equal to F of T is exactly the exponential times T of that matrix. So the only continuous, so we saw up here, let's see, so I'll let you write it down first, and then I'll count to 5, 4, 3, 2, 1, and then I'm going to browse up. And so we saw these relations summary before. So these are exactly the properties you would expect when you see a group homomorphism going into the real numbers, taking plus here to multiplication here in the group and inverses to inverses. And what this result says is that if you want the group homomorphism going from the real numbers into your matrix group, then it is the exponential, and you want it to be continuous, then it is the exponential of some matrix. Those are the only such group homomorphisms. So if we do an example, the F we had before, if we identify, so in had before, in previous example, if we identify GL 1 and 0 with just R. So remember, I took the positive numbers under multiplication. That's just the same as doing the real numbers, where you identify a number with its exponential with certain not small r with the real numbers. Then we can describe this map, which sent, let me write it with T in order for it to match. So our map was that it sent this one to E of T 0, 0, E of I, T, S, where S was irrational. But as irrational or not, this can then be written as the exponential of T times the matrix I, 0, 0, I, S. So all such homomorphism, they can be written in this way. See, so the final result I actually want to prove because it uses one of the things that we proved in the very first lecture. And we're also going to use it when we need the Lie algebras, which is that for any x in, well, complex, let's say the complex matrix, a real matrix is a special case of a complex matrix. We have that the determinant of e to the power x will then just be the trace of the matrix that we're exponentiating. And here is one of the nice cases where because we have this idea of continuity, we get it to cheat a little bit from the algebra and then just assume that our matrix is diagonal. So we assume first that x is diagonalizable. So x is some C, D, C inverse, where D is a diagonal matrix with these numbers on its diagonal. Then we, from last time, we saw that the exponential map will then just be e to the power d inverse. So, and then e to the power d for diagonal matrices, that's very simple. The exponential of a diagonal matrix is e are just the individual number exponentiated. And yeah, we didn't talk that much last time about like how to actually compute the exponentials. but this is one of the most common ones. If you can actually diagonalize it, then you can use that diagonalized form, and then you just take the exponential of this diagonal matrix in the middle, and that will just be the exponential of the individual numbers on the diagonal. If we then take the determinant of Ex, that's the same as taking the determinant of D, because they are just a basis change away from each other. And the determinant is independent of choice of basis of your vector space. And okay, and that's just a diagonal matrix. So for a diagonal matrix, the determinant is just all the numbers on the diagonal multiplied together. Which then become the sum from the normal reversal of the exponential. And the sum of all the eigenvalues is the trace. So, so this is for the case of the diagonal matrix. We just use that we can explicitly compute the matrix exponential. And then if X is not diagonalizable, take sequence X, let's say, what did I call it? XK, converging to X, where each XK is diagonalizable. Then we have shown that the determinant of EXK is equal to E trace XK. And then we take limits using that determinant, trace, and exp is continuous for the results. So this is sort of a nice thing now that we actually have some idea what it means with the distance and topology and continuity and stuff, is that we don't really need to deal with the non-diagonalizable matrices and do some sort of upper triangle decomposition or Jordan decomposition or anything like that. We just do the diagonalizable, and then it's by continuity, that's enough. So yes, so we're back for the second topic related to matrices, which is polar decomposition. And as I said, with this suggestion notation here, what we want is something similar to the polar decomposition in complex numbers. And in particular, we have this nice subclass of complex numbers where you have like logarithms and square roots and stuff, which is the real numbers. And we want to do something, or the real positive numbers. We want to do something similar for for matrices. And sorry if this is going a little bit fast if you're watching the recording, because I forgot to record it the first time. And so what we're going to try to do is the suggestively here, this is a complex number of length 1, but we're going to see that as a unitary matrix of a 1 times 1 unitary matrix, which you can find the definition for here. And then this E to P, where P is just a real number. Or actually, I should call it X for later, but okay, never mind. So what we're going to do is now a lemma. Now, so yeah, going to need another definition first. Definition, one very quick definition. If P is alpha joint, we say that P is positive. Some would say strictly positive, but let's go with positive. If V, P, let's say we need a dimension on this, so M and C, let's say. P times V, P like this, taking the inner product, is strictly positive for any V in the n-dimensional complex space not being 0. So we have first this definition of being self-adjoint, and then we call it positive if whenever we take the same inner product and multiply it on the other side, we still have something positive. So sort of we are able to modify an inner product and with the matrix P and still keep it positive. So then we have the following results. So we start with a lemma. So
I have a quick question, Alan. So,
yes.
So this inner product, if we take a general matrix, this does not need to be real valued, right?
No.
So this is special for the self-adjoint.
Yeah. So
or is it only in this special case? So we say it's real valued and it's positive. So
yeah, no, this is special for the self-adjoint matrices. So yeah, let me answer that question. So note V is always real valued when P is self-adjoint. So thank you, Anna. So why? Because this, if we have an inner product with a matrix, for the complex inner product, we can move it on the other side if we take the conjugate transposed. And since it's self-adjoint, it's the same. And right, then for the complex inner product, flipping things around means taking a conjugation. So it means that whatever number this is, it's equal to its own conjugate, and that's only the case for real numbers. So, so in particular, this is going to be apparent now in the proof. But because of this, self-adjoint matrices only have real eigenvalues. So they don't have complex eigenvalues, even though there are complex matrices in general. So let's see exactly that. So that's actually the first result, is that a matrix X is self-adjoint if and only if it can be written as a unitary matrix times a diagonal matrix and another unitary matrix, where so the conjugate transpose of that unitary matrix, which is also its inverse. D is then a diagonal matrix with this on the diagonal. All of these are real. And U is then, so this is, let's say, maybe I should come up with some curly U to see the difference. It's easier on the computer when you have italicized and non-italicized U's, but okay. So U is then, and U is a unitary matrix. So this is the first result, is that all of these self-adjoint matrices are have real eigenvalues, and they are diagonalizable in. And what you should think about this unitary matrix as saying is that if you switch to an orthonormal basis of your space, that's what the unit matrices represent. They are an orthonormal. They are columns are an orthonormal basis in the complex space. So if you switch to you can switch to another orthonormal basis, and then it will just look like a diagonal matrix with real values on the diagonal. Then B, P self-adjoint is positive if and only if it only has, let's say, strictly positive eigenvalues. C, if X is self-adjoint, then e to the power x is positive and self-adjoint. And finally, if, what should I call it? Curly P? Does that look different enough from the usual P? Or let's say self-adjoint plus something like this. A star is equal to A positive. Yeah. Let's see. And now I actually need this to be invertible. No, never mind. Let me not write it like this. So let's do the following. If P is positive and self-adjoint, there is matrices Q. Let's say there are unique matrices. Q, which is we can write as a square root of P, and X, which we can write as log of P. Q is self-adjoint and positive. And X is just self-adjoint. Such that Q square is equal to P and e to the X is equal to log. No, sorry. It's also equal to P. So summarizing these statements, what we want to think about is sort of the positive self-adjoint matrices sort of taking the role as the real numbers have in the inside the complex numbers. So you can think of this idea that these positive, these self-adjoint matrices are not the real matrices, but they are the matrices that look real in some orthonormal basis. That's the first result, is self-adjoint matrices are the ones that look real in some orthonormal basis. Furthermore, the positive ones are the ones that have look like they have just positive diagonal values in some orthonormal basis. And then just like the exponential map takes a general real number and maps it to positive real numbers, the exponential map takes a self-adjoint matrix and maps it to a positive and self-adjoint matrix. And just like real numbers have positive real numbers have well-defined square roots and logarithms, where the square root is also positive, where the logarithm in general might not be positive. This is the same for these self-adjoint and positive matrices. And here I did the square root, but you'll see from the proof that I can do any kind of root that I want. Are there any questions to the statement before we continue with the proof? Okay, then I'll do the proof. So result from appendix, either book or notes. says that if matrix is normal, that is yes, A commutes with the conjugate transposed, then A can be written as a equal C, or we should have written X probably, sorry. I'll write this as X. X transpose, then X can be written as X, C, D, no, not, that was the entire point. U, D, U star, where U is a unitary matrix and D is diagonal. So so you have this concept of normal, which is just a general linear algebra result that yeah, if you have if you are normal, then you can be diagonalized in some sort of orthonormal basis, which means that you can be written on this form. So there's lots of matrices that fall into this category. So like self-adjoint matrices are one. So the real equivalent to a self-adjoint matrix is then a symmetric matrix. So you know that you can diagonalize a symmetric matrix in an orthonormal basis. This is also a special case of this. Orthogonal matrices, then it becomes the inverse. That means that in particular they commute, so they are also normal. So there's a whole class here, but in particular, so in particular it holds for X self-adjoint. So this helps us almost all the way there. Now we just need to show that this diagonal is real. Furthermore, since X is equal to X Y the conjugate transposed, and the conjugate transposed, it will then be switching the order and taking the transpose. So it will be U conjugate transposed, D conjugate transposed, and then U transposed, which is U D star U. It follows that D must be real, right? Because we got the same result. Sorry, I forgot the conjugate transpose at the end there. We got the same result. So if I switch to some, so the first part says that if I switch to some orthonormal basis, then X will look like a diagonal matrix. And then it will look like also the conjugate transposed of that diagonal matrix, which is just the conjugate for a diagonal matrix. There's no transposed. So I can write this. So this is exactly just the same as just doing the conjugate, since it's a diagonal matrix. And so since it both has to look like D, and the conjugate of D, it has to be real. So that's the first part. And then conversely, if x is equal to u, so now what we showed is that if it was self-adjoint, then it has to be on this form, and then conversely, if it's on this form, then it is self-adjoint by direct computation. So use, for example, use one, let's call this equation 1. So it's just use that equation and you compute directly that it's self-adjoint. So if P is self-adjoint and positive, write P equal U D U transposed, where U is U1 dot UN, which is an orthonormal basis. And let's say that D, let's call the diagonal entries mu. Right? And then we write V equal to, right, an arbitrary V as the sum from 0 to n of Vj, Vj, Uj. So V to the power to j, which is, I should probably write it down since we're not doing tensor analysis, so no one gets confused. So where this is a complex number, right? So I know that P has a decomposition like this with a unitary matrix. That unitary matrix comes with its own orthonormal basis, and we're going to use that to decompose any vector into that orthonormal basis. Then V P V will just be the sum from J. Well, I can write it like this. It would just be mu1 V Bj square plus mu2, no, sorry, not Bj square, but V1 square, V2 square, and then finally mu n Vn square. So if I write everything in this orthonormal basis, then it just becomes this diagonal matrix. And and then what happens if I multiply with this diagonal matrix is just that I get mu1 times the first part, coordinate mu1 times the second coordinate, and so on. And this is positive for any v1, vn non-zero if and only if all mu j are larger than 0. So essentially, it's just a change of basis to the one where it's diagonal. Any questions so far before I continue? So the next thing we're going to do is we're again just rest of the proof is just using this diagonalization and basically do what we would do with the real numbers just in this diagonalization. So so this is, let's say, this was was A. This is B. Now for C, this is simply the fact that if X is U star, then E to the power X is U, E, D, U star. So that's what we just talked about, the fact that we can just compute the exponential by just using this diagonalization. And okay, so, and then if D is lambda 1 to lambda n, then ED is just the exponential map of these things here. And these are all positive. So that's simply C is just using, again, we're just using what we would do with the real numbers, but in this basis. And then for D, we're essentially then doing the same thing. So here I'm writing P as U, D, U star. So I'll try to use these mu's to indicate that they are positive. So I should write diag here, probably here as well, and here. So if we have something on this form here, then if I define then Q as U, and then I'll write this as square root here, U star, where this thing is just a diagonal matrix where we take the square root of all of these numbers, and I define my X as U log D U star, where this log D is just taking the logarithm of all of these numbers. So I'm just doing what we do with real numbers, but in coordinates. Then Q square is P. EX is also P, because we're just, these behave very nicely under conjugation with both doing squares and doing exponential behaves nicely with respect to conjugation of another matrix. So that is so that shows existence for uniqueness for uniqueness, we note that if Q tilde equal to U tilde D tilde U star is any other such matrix, with Q tilde is equal to square is equal to P. Then it must have the same eigenvectors as P, since Q tilde square is U tilde D tilde square U star tilde, which is then has to be equal to U D U star, and it's clear that here columns in U are eigenvectors. Here in U tilde eigenvectors. So that means that if one, so it means that the columns, hence the columns in U and the columns in U tilde, they have to be the same because they have to have the same eigenvector. So theoretically, like if you have a repeating eigenvalue, for example, you could have a case where they flipped one of the, in the U tilde, you flip one of the columns around, but you need the same eigenvectors and d tilde square must have the eigenvalues of d, and that means that q tilde has to be equal to q. So if the diagonal square has the same eigenvalues, then it must be equal to the eigenvalues of this square root that we defined here. So if the square becomes the these eigenvalues here, then this square must have the same eigenvalues. Then so again, we could perhaps switch one of the columns, and that means that the eigenvalues maybe come in a different order and stuff like that. So the diagonal matrix, instead of looking like 1, 2, 3, it might on the diagonal it might look like 3, 2, 1 if you use a different basis, but it's still the same eigenvalues. And then if two matrices have exactly the same eigenvectors and eigenvalues, and it's a complete set of eigenvectors, you have n eigenvectors, they're the same and the same eigenvalues, then they're the same. So it's essentially so it's then the same matrix because they need to have the same eigenvectors with the same eigenvalues corresponding to that vector. Let's say of d and, well, let's see, how do I write this? That they need to correspond to the same vector. Right. So same eigenvalue for same eigenvalue for same eigenvector. And so that means the q tilde is just a way to rewrite the q, and it's the same argument for x. And it's continuous by construction. Meaning that if I define these maps and then do a sequence of them, then everything will work out nicely in this sequence. So that gives me the result I want. So then next time, we're going to show that any matrix can be written as U, E, X, where X star is equal to X and U is unitary. So that's, and this is unique. So invertible G, L, and C. So this will be like the highlight what we're going to look at next time. This is the polar decomposition, where we sort of get a way of manipulating it because we have like a standard form where one part is unitary and one part is this positive that sort of works like positive numbers where we have square roots and logarithms and stuff like this. So that's it for today.